awarded by the International Society for Bayesian Analysis. On the topic of non-parametric Bayesian methods, so great to have Tamara here, and Mike, of course, needs no introduction. He's been a pioneer in many, many areas in machine learning, including non-parametric Bayes. He was a fellow of just about everything. And,
Thanks.
And he'll stop me there.
So we've got 4 hours. Just a couple words about the agenda. So we're going to alternate back and forth. I'm going to do some whiteboard math kind of stuff, and Tamara's got some beautiful slides with colors and all. So we'll kind of, a little mix of something a little bit elementary and something a little advanced to kind of make sure everybody gets something out of it. Just 2 words about this topic. It's rather different from a lot of the other areas of machine learning. So I've become much more of a theoretician in the last 10 years. In fact, I consider myself really a theoretician now. And when I'm doing the theoretical work, it's almost always on optimization problems, like many people, like many of you. So asynchronous, distributed, accelerated, and all that. There's well-stated problems, and you can start to solve them, and many of us have. This topic, there is a lot of theory. In some sense, but there's much to do. It's more open. There's just not as many obvious problems to work on at some level. We're probably not going to write down a lot of theorems. The theorems are almost all statistical. And they're quite deep. There are things like this thing converges, and here's the rate, and here's the limiting distribution. Kind of the full spectrum of things you might want. So what are called Bernstein-von Mises theorems exist in this area. So that's stronger than you get in most of the optimization stuff, where you don't know the limiting distribution. If I run the lasso, what's the limiting distribution of the coefficients? There's some work on it, but it's much stronger here. But that's statistical theory, and I assume most of you are computer scientists. Here's an algorithm, here's its rate, or here's some property of the algorithm. The algorithms here are not the important part. The important part is the mathematical structure that leads to certain classes of models. It's a very expressive modeling language. So in practice, using these kind of things, and I do in consulting, you talk with the person, and you think about all the components of the problem, and you write down a bunch of modeling pieces, you put them together with this formalism. The underlying math here is stochastic processes. And we will talk about the Levy-Kenshin theorem a little bit and the Palm calculus, which is the real math underlying. So this is actually much deeper math than I'm used to in optimization, where you write down a linear functional plus a regularization. You're kind of done with it. And then you start calculating with Lipschitz, right? This is going to be a day of kind of some math. It's stochastic processes, and it's links to combinatorics, to algebra, to functional analysis. And that's what you need to learn to work on this topic. And once you can learn that, you can write down models, and you can then apply standard algorithms to them. The algorithms are slice sampling, Gibbs sampling, hybrid Monte Carlo, and so on. And then, as a theoretician, you sort of throw up your hands because you can't say much. All right? But that's the opportunity. These are highly combinatorial problems, so much more expressive than just a linear separator or something. And so if you're used to kind of Sanjoy-style work on mixture models, that's probably the path to start to go, to get to say more from a computer science point of view about these things. But these are much richer than Gaussian mixture models. Okay, so just a little context though. So you're not going to see algorithm and analysis of algorithm here. Open up your soul a little bit to the, a slightly different area. This is, interesting math. And start to perceive the combinatorics and the stochastic processes and the random measures and how they all interact. That's the beauty of it. So speaking of the beauty of it, Tamara is a very beautiful lecturer, so let her get started.
Great, thanks, Mike. So this first lecture is really going to be about understanding why we even want non-parametric Bayes. What is it doing for us, and sort of getting the intuitions behind it. And then we're going to dive deeper into the math in the second, third, and fourth lectures today. So at a very high level, non-parametric Bayes is really about learning more from your data as you get more of it. And so I really want, at the end of this hour, for you to be able to understand, what exactly that means. So this is just part one. And so there are 2 parts to non-parametric Bayes. There's we're doing Bayesian analysis here, and it's non-parametric. And so the Bayesian aspect is saying, okay, we're going to build up a generative model for our data. We're going to say, oh, we have some hidden parameters that we're interested in learning, some latent parameters. We have some distribution over them that expresses our knowledge going into the problem. That's our prior. We have a distribution of our data given our parameters. That's our likelihood. And so this sort of builds up a model of what our data would look like given our parameters and what our parameters look like in general. And then Bayes' theorem tells us how to invert that, to say, OK, well, what we've actually seen is the data, and what we don't know is the parameters. And so what is our state of knowledge of the parameters given the data? And so this sort of reinforces what Mike was just saying, that what's really important in this analysis, or at least certainly one component of it, is understanding this generative model for our data so that we can then apply Bayes' theorem to actually apply our algorithms and so on and get out results from that model. Okay, so now the nonparametric part here isn't sort of this classical frequentist definition of nonparametric. In the context of nonparametric Bayes, we're not saying we don't have any parameters. In fact, we're saying quite the opposite. We're saying that we have a growing number of parameters in our data. And the way that we're going to get this growing number of parameters is to have an infinite latent parameter. And so at this point, it might be sort of odd to say, oh, how do we have a growing number of parameters at the same time as we have an infinite parameter? And again, that's one of the questions that we're really going to answer during this first part, this first lecture. How can we have those things at the same time? But to get a sense of why we would want a growing number of parameters, think about how you use Wikipedia. Well, at least I can tell you how I use Wikipedia. So I was recently reading this book, A Long Trek Home, and it's basically about this lady, and she starts from Seattle, and she sort of hikes and paddles her way up to Alaska, and it's sort of really fascinating. And once I've read it, I sort of go on Wikipedia to learn more about the book and more about her, and I find myself reading about Alaska, and then that takes me to another link about the Pacific Rim, and soon I'm reading about plate tectonics. And you can sort of spend all day on Wikipedia doing this, right? You can just say, oh, I'm going to read article after article, and I keep learning something new. And this doesn't just stop after a few articles. You really find that sort of, no matter how many articles you've read on Wikipedia, there's always new topics to explore, new topics to learn. And so the point I want to make is, let's say we're doing some topic analysis of Wikipedia, we're discovering topics, we might be under the belief that no matter how many articles we've analyzed with our algorithm, there are always new topics that we could discover beyond that. And so I like to think of this as some sort of Wikipedia phenomenon, but it's not specific to Wikipedia. There are tons of areas where this comes up. Another one is species discovery or species sampling. It's sort of amazing, humanity has been trying to discover new species for a very long time now. It's not like we're not going out there and actively getting these new species, and yet if you Google new species any week, you'll find that in the past week a bunch of new species were discovered. They're still being discovered all of the time. The new species in general aren't necessarily that cute. I kind of like this flapjack octopus from one time I was Googling new species, so I put this one up. But you'll find probably different ones in any given week. Okay, if you ask all of your friends what exercises they're doing, you'll probably discover new exercises as you ask more and more friends. If you analyze social networks, it's likely that as the social networks grow or you analyze more of a social network, you'll find more friend groups, more interest groups, more different sort of components of that social network, more to learn as it's growing or as you're learning more about it. If you look at images, you expect to find more unique objects in those images as you get more and more images. If we're doing some sort of genetic analysis and you're looking at people's genomes, you can find more and more unique ancestral populations as you see more and more genomes. If you're looking at newborns entering a hospital, or really anyone entering a hospital, you expect to find more unique health issues as you examine more and more of this population. Even if you're just doing something like survival analysis, you can see more groups and more different behaviors as you analyze more individuals, or something like density estimation. Maybe if you have a few data points, a Gaussian might be an adequate model for that. But as you get more and more data points, you want more nuance, and you might find that you have something that requires more and more nuance to really express what's going on with that distribution. And so for all of these reasons, we might want a growing set of parameters as we get more data, basically to express more nuance in the data. Okay, so that's going to be the idea of nonparametric Bayes, and again, during this hour, we're really going to get more of a sense of exactly how that works in practice. What do we do to get these kinds of models and this kind of behavior? And so I'm going to focus on a particular example problem here, clustering or mixture models, as Mike was saying. And a particular nonparametric Bayes model that we're going to build up to, the Dirichlet process. Now, this is not the entirety of nonparametric Bayes, and hopefully in the remaining 3 lectures, you'll get a much broader sense of what's going on. But I think by focusing in on this application and this model, you're going to get more of an intuition about what we're trying to accomplish in general. So the big questions that we're going to try to answer and have answers to by the end of this are, why nonparametric Bayes? We've got a little bit of an answer so far, but what are the models that are giving us the kind of behavior that we were talking about? What does it mean to have a growing number of parameters and an infinite number of parameters, and why is this helping us accomplish some sort of particular inferential goal? And why is this something that is challenging, that we need to devote some energy to making it work, but at the same time practical, something that we believe we can actually get inference algorithms from, et cetera? Yes, this is a question.
I'm coming from a completely frequentist point of view. And
Sure.
I just want to compare to an analog. This is like structural discrimination, that I first consider linear models, then quadratic models, and then polynomials of higher and higher degree, and I have this kind of embedded.
So my big answer here is that I would say that the answer to what is this like will be very much answered by the end of this this hour. But you're going to find that this is actually a stationary model. We have a single model, and this allows us to get the growing number of parameters. But maybe keep in mind your question, and then we'll see at the end of the hour if you feel like it's been answered.
Maybe just one quick question. That's selecting a model. This is averaging over all possible models at all cardinalities. So that may help.
I'll also say when we look at a particular growing and infinite number of parameters, you'll find that the underlying model isn't changing. It's what we're inferring about that model. But I think after an hour, this will be much more clear. OK, so let's start off with this particular example of clustering. So we have a collection of data. Remember, in clustering, we want to assign our data points to one and only one group. That's the nature of the latent structure that we're trying to find in clustering. And so a natural Bayesian model for this, where again we want to say how this data could be generated with some set of latent parameters, would be the following. So first of all, let's think about what our latent parameters would be. Well, usually when we're trying to do something like clustering, when we have something like a Gaussian mixture model, our parameters are something like the centers of the clusters. They might also be the shapes of the clusters. I'm just going to go with the centers just because that's an easier story for me to tell right now. Nothing changes in this story if I add the shapes as well. Also, the assignments of data points to clusters are another set of parameters that we would be interested in. OK, so once we have these two parameters, we can say what our likelihood is, the probability of our data given our parameters. And so typically this would be something like, OK, let's generate our data points normally distributed around the center for a particular cluster with some shape, some covariance matrix. Now, if we're being Bayesian, we also have to put down this distribution, this prior distribution over the parameters. And so a natural prior, maybe for the centers, would be to say that they're normally distributed. And then a natural prior for the assignments of data points to clusters, well, we don't really know what percentage of data points come from each cluster to begin with. So let's put down a distribution over that. Let's say that the percentage of data points in the first cluster is beta distributed, because that's a nice distribution that gives us a value between 0 and 1. And then let's say we have row 2 for the remaining mass, what goes to the second cluster. And so then finally, we're going to have a categorical distribution. We're going to say for each data point, the nth data point, we choose that it belongs to cluster 1 with probability row 1 and cluster 2 with probability row 2. Yes?
So stupid question. So why actually the beta distribution is the right distribution to use?
So I don't want to say that it's the right distribution, but it's certainly a very convenient distribution. And so you can ask yourself down the road, was there a better distribution that would make sense? But this will cover and put some probability mass over all possible row 1s. And it has a number of convenient computational properties like conjugacy with the categorical distribution. So I'm going to choose the beta. And if anything, I think this is going to be a recurring theme in this particular hour. Let's make convenient choices that give us some probability mass over what's going on. But I think a general question that you would absolutely want to ask in actual research is, are these appropriate choices? And can you make better choices that maybe have better properties? Yeah.
U0 also comes from a distribution, or how do you pick?
Yeah, so this is a classic problem in Bayesian analysis. When do you stop putting priors on things? For the moment, let's just assume that we have mu0 and sigma naught, or we feel pretty confident about what we might put there. Just because the focus of this particular tutorial is going to be on the nonparametric Bayes aspect, which will be basically sort of digging down deeper into this beta distribution. But again, you could think more about your prior choices, and that's a whole area in and of itself. OK, great. So as I said, let's suppose that we're pretty comfortable. This is a reasonably standard mixture model in general, and we're pretty comfortable with all of this. But let's review the beta distribution in particular, at least to know what assumptions that we're making for the moment. OK, so recall that the beta distribution has this form where we have the gamma function here. And we have some distribution, some density over the row 1s here. We're generating a row 1 between 0 and 1 because we want to interpret it as a probability. And A1 and A2 are hyperparameters of this model. And so let's just recall, if I set A1 and A2 to 1, you can see that I'm going to get everything being taken to the 0 power, and so I'm going to get a uniform distribution over row 1. If I set A1 and A2 to be greater than 1, then we get this yellow curve here, which is starting to peak. If I set A1 and A2 to be less than 1, then we're going to get this green curve, which is starting to put more mass on the edges. And so let's just start asking what happens at certain values of the A's in order to better understand the beta distribution. And even if we're all very familiar with the beta distribution, it may be the kind of thing that we tend to look up on Wikipedia when we need it. And so let's just make sure we have our intuitions very much at the fingertips going forward. OK, so the first thing that I'm going to do is I'm going to draw row 1 and row 2 according to beta 1, 1. So I'm abusing notation a little bit here. Row 1 is really what's being drawn according to beta 1, 1, or the uniform distribution, and row 2 is 1 minus that. But I hope you'll bear with me on this. And so what I'm doing here is I'm just plotting row 1 and row 2, and as we expect, these are uniform draws. In fact, both of them are uniform draws. And so we get draws that look like this. And so the question that I want to ask you, first of all, is, let's say I replace my 1 as the parameter here with A1 and A2 equal to some very, very small number, like 0.01. What's going to happen? What is exactly 0, 1 meaning?
Extreme.
Yeah. Great. OK, so the observation is that I'm going to get extremes. I'm going to get all of my mass going to either 1 or 2. And so I'm generating a random distribution still. It's just that the distribution that I generate is pretty boring. It says, basically with probability 1, I'm going to choose 1. Or with probability 1, I'm going to choose 2. But it's going to put all of the mass on one or the other. And we can see that this was going to happen, if we were looking back at this distribution here. When we choose smaller numbers, we tend to get more and more mass at the extremes of rho. OK, and so now, what if instead I choose, 1,000 to be my parameter? It's shared between A1 and A2. Then what am I going to get?
A much more even distribution?
Right, a more even distribution. In fact, I'm going to get the uniform distribution. And so now instead of a uniformly distributed row 1, the random distribution that I'm generating is itself uniform over 1 and 2. So I'm generating these random draws, but they're all basically the same. They're just a uniform distribution. OK, and then finally, let's say that I choose A2 to be greater than A1. Like I choose beta 1, 5. What am I going to get there? See many people using their hands to describe something, which is awesome. Does anybody want to say something out loud, possibly with the help of this thing? So here, red is beta 2, 5. Yeah.
1,000, almost certainly it's a half, plus or minus 1 in the square root of 1,000 or so.
Sure. But now let's say I have a beta 1, 5. What's that going to look like when I make draws from that?
It's going to look like 1/6, 5/6 plus or minus some.
Right. So it's going to tend to have the row 2 have more mass, which is even less precise than what you're actually telling me. So let's just take a look at that. OK, so here I'm drawing from a beta 1, 5, and you just notice that on average, row 2 is getting more of the mass here. OK. So that's the finite Gaussian mixture model where we have 2 clusters, but of course, in general, we would have more than 2 clusters. We might have something like k clusters. And so what would the generative model there be? Well, it would be pretty much exactly the same thing. We would choose our mu k's according to some prior distribution. Maybe I'll just say it's the same prior as before. So these are our cluster centers. Now we choose our cluster proportions again. We want some probability on each of our clusters. And we need a distribution besides the beta. And the natural generalization of the beta is the Dirichlet distribution. And so here, if we have 3 clusters, we'll do a Dirichlet over 3 elements. Again, we choose each data point to belong to a cluster according to the categorical distribution. So it belongs to cluster 1 with probability rho 1, cluster 2 with probability rho 2, cluster 3 with probability rho 3. And then finally, we generate the actual data normally distributed around whatever cluster center that data point was assigned to and with some shape that we've determined beforehand. OK, so again, let's dig a little bit deeper into the Dirichlet distribution. So it looks much like the beta distribution. We have these gamma functions here for a normalizing constant. We have exactly this rho to each hyperparameter as we did before. All of our hyperparameters are greater than 0. And now we're generating our probabilities such that they're all between 0 and 1, and they add up to 1. So they're on the simplex. OK, and so we can ask the same questions we did before. What does this actually look like? What behaviors do we get? So for instance, if we choose our hyperparameters to be less than 1, then we're going to get peaks around the edges. If we choose our hyperparameters greater than 1, then the mass will concentrate in the middle. And if we choose our hyperparameters not to be symmetric, then we won't get a symmetric distribution. OK, and again, we can ask what happens here. So in particular, let's say that I draw from a Dirichlet distribution where all of the hyperparameters are 1, what distribution is this? Uniform on what? Right, on 4 items. But so for instance, is rho 1 going to be uniformly distributed? It was when we were doing the beta distribution. I see a no. Any particular reason why? Any more intuitive reason why? Yeah.
Oh, be beta 1-3.
Right. This is essentially beta 1-3. Another way to think about it is this whole thing is uniform over the simplex. It's not uniform over each one of these being 0, 1. And in general, when we have to add all of these up to be 4, that's not going to be uniform on any one particular one of them. And so if I make a bunch of draws of this, you'll see that any individual rho 1 is not going to be uniform, or any of the individual rows won't be uniform. They'll tend to be lower. OK, so similarly, if I have all of my A's be small, I'm going to get a similar behavior to what we saw last time. I'll see that we're basically picking out one of the rows to have all of the mass. And finally, if I have all of my A's, all of my hyperparameters large, then I'm going to generate a uniform distribution over the different clusters. It's just going to be a uniform distribution now over 4, and so they'll all have mass 1/4. So far, I've assumed that the number of clusters is much less than the number of data points. How was it that I assumed that? How do you know that I assumed that? So k was fixed, but k could be fixed, and I can have way more data points than any particular k. Was there, let's think back to my illustrations, like when I had the little pictures of, oh, here's a bunch of data that I generated from clusters.
There could be many empty clusters that we didn't show us.
Yes, exactly. So what we assumed was that we were seeing all of the clusters in the illustration, at least implicitly. Maybe you weren't assuming that. Maybe you were thinking, oh gosh, there could have been so many empty clusters that we're not seeing. But what I was assuming was that we were seeing every one of the clusters. There were data points in every one of the clusters. I had this cartoon where I said, oh, here's a little cluster of data points. Here's a little cluster of data points. Here's a little cluster of data points. We have 3 clusters. we saw data points in all of those clusters. Now, in general, if I had had 1,000 clusters and I had made 100 draws, clearly I could not have had a data point in every one of the clusters, and that would have had a much different illustration. Yes?
Something that confused me, probably because I'm so far from being Bayesian, but I view clustering as given data, I try to find a model. And here you're saying, given the model, how will the data look like?
Right. So this comes back to this original point I made that usually what we're doing in Bayesian inference is we're saying, let's make a story about how we would generate the data given the parameters and then the parameters as well. And so this is a generative model. It says, here's a story of how I could simulate data. And then Bayes' theorem is what's going to turn that around and say, OK, here's the probability of the parameters given the data. And so what we're doing right now is we're just exploring that story. We're exploring its assumptions, because if it has the wrong assumptions or whatever its behaviors are, we're going to capture those behaviors again when we turn things around.
There's another literature this makes contact with. Don't just think clustering, think species sampling.
Sorry, what
Mathematics
sampling?
is the same.
Species sampling.
You're going onto an island and you don't know how many, you start collecting organisms, right? You don't know how many types there are, how many species there are. And you see a few instances of giraffes.
Like the good Turing.
It's a good Turing. So there's a lot of good Turing behind this, and you'll see connections to that if you know good Turing. So clustering's one application and metaphor, but species sampling's another one we would have in mind where she is now, that we're exploring species sampling.
Right. So we're just looking at this one particular example to ground it in a particular application, but there are a lot of other applications. OK, so indeed, species sampling is another example of where we might care about this. So the point that I'm trying to make here is there are a lot of cases where we'd imagine that some of our clusters aren't filled in yet. In actual application. So as I mentioned in the beginning, we're going out and we're sampling these species, and there are plenty of species we haven't sampled yet. We know that that's probably true because we're getting new ones all the time. It seems likely we're not going to run out today. But same thing with topic modeling. You go out and you're looking at topics, and you don't think that we found them all, like right now, today. Yesterday we hadn't. There were still new topics to discover, and that's probably true tomorrow. Same thing with groups on a social network and so on. It seems like there are probably empty clusters out there, clusters that don't yet have data points in them and that we're still trying to discover. And so it behooves us at this point to make a distinction between components, which could be like a number of latent groups, and clusters, which could be the number of components that are actually represented in the data. So for instance, if I had 1,000 components here, and I sampled 100 times from it, I'm going to have fewer than 100 clusters, but I'll still have 1,000 components. OK, so let's see this in action. OK, so here what I'm doing is I'm just drawing another Dirichlet distribution. So in those first two slides, I had row 1 and row 2 drawn from a beta distribution. So I drew from 0 to row 1. That was probability row 1. And I drew from row 1 to row 1 plus row 2, which happened to be 1. And that was the result of the beta distribution. I did the same thing with the Dirichlet. Here was a sort of region of size row 1, a region of size row 2, et cetera. And now I'm doing this again for now row 1 to row 1,000. And it just happens that some of these rows are so tiny that we're not seeing them all. But I'm still making a draw from a Dirichlet distribution, and so I'm getting 1,000 probabilities here. If there's anything unclear about this illustration, just please do ask.
What is n?
Right, so great question. I'm about to start making draws from this Dirichlet. And so far I haven't met any, so n is 0. K is the number of components here. You can think of it as the number of clusters. And so I'm about to make a draw. And the way that I can make a draw from this distribution, of course, is I could make a uniform random draw on 0 to 1. I'll put down my uniform random draw wherever it lands, and that will choose one of the components. And so at this point, I have one data point. It belongs to one cluster, and I have one cluster, whichever that data point belongs to. Now, I'm actually coloring the clusters that data points fall into blue. It happens to have fallen into such a tiny little component that you're not seeing that. But let's see if we make another draw if that will happen. Okay, great. So I've drawn a second data point from this distribution. So I drew this random distribution, and then I drew a data point. I drew an IID uniform random variable to say, OK, the second data point belongs to this component. Now I've colored this component.
Tamara?
Yeah.
Could you explain what does that band mean? I don't.
Yeah, great. Let's go over this again. So what I'm doing is I'm drawing from 0 to row 1, and then I'll draw a line at row 1. And then I'm drawing row 1 to row 2, and I'll draw a line at row 2. And I'll draw from row 2 to row 3, and I'll draw a line at row 3. Now, some of these are just such tiny little intervals that you're not seeing the interval, but there are technically 1,000 lines here, or I guess 999. And then what I'm doing is I'm saying whenever I choose a particular component by making a uniform draw. So the key realization to say here is this component has probability row 800. And so if I make a uniform random draw, the probability of that uniform random draw falling into this component is row 800, because that's the length of this region. And so if that interval has probability row 800, a way that I could draw from this distribution is to make this uniform random draw, see what it falls into, and that's equivalent to making a categorical draw and saying, I'm drawing 800 with probability row 800. Sedoes that clarify?
What's a categorical draw? Could you say that?
Oh, right. So the categorical draw, it takes as its input a sequence of probabilities that add up to 1. And we say that we draw 1 with probability row 1, 2 with probability row 2, up to k with probability row k. Yeah. And so what I'm going to do is I'm going to color each region, each component that gets filled in by a data point blue. And so I've technically done that twice already. It's just the first one was very, very tiny. OK, so I'm going to do this again. And I keep drawing these. And we see that this probability mass is filling up pretty quickly. And as I make more draws, it seems like we're getting pretty close to having everything filled. So, am I pretty close to seeing all of the components?
No.
No.
There might be a whole bunch of like really small.
Right. There might be a whole bunch of really small ones. And in fact, I can guarantee you that there are at least 900 components that we haven't seen yet. Because I've only made 80 draws. I can at most have filled in 80 clusters, and I probably didn't even do that. And so even though it looks like we've filled up a ton of mass here, there's actually at least 900 components we haven't seen.
Just a math quiz for somebody. The number of components you filled in is roughly log 80. If you want to start to do that calculation in your head, you'll be ahead of the game later.
Exactly.
It doesn't matter.
We'll get into that.
Yeah, let's actually, without doing that calculation explicitly, let's get a little intuition with another drawing of how this might look. So here what I'm going to do, to again prime you to actually do that calculation. So I'm going to plot the sample. This is like the data point. So on the first data point, we're looking at right here. And over here, I'm going to plot the cluster number. So the way that I'm going to order my clusters, the way I'm going to label my clusters, which aren't, again, the same as my components, is I'm going to say the first cluster, the first component that a data point falls into, that's the first cluster. And anything else that joins that, it's joining the first cluster. Now, if anything else joins a new cluster, the first component beyond the first cluster that is joined, that's going to be the second cluster. So there's only two options there's only one option for the first data point. It has to join the first cluster. And there's only two options for the second data point. It either joins the first cluster or it joins the second cluster. OK, so let's see what happens to the second data point. And the way that I'm doing this is I'm doing this exactly what I did last time. So in that illustration that we just saw, I drew row 1 to row 1,000 from a Dirichlet, and then I made draws from that with my uniform. I'm doing the same thing here. I drew my Dirichlet, so I got my random row 1 to row 1,000, and now I'm making categorical draws from that, and I'm saying, what is the cluster assignment of each of these? OK, so data point 2 belongs to a new cluster. Data point 3 belongs to a new cluster. Data point 4 shares a cluster with 3. And something you'll notice here is that the number of clusters that have been realized in the data so far is the maximum number on the y-axis that we've seen. And so if you think about looking at a line over all of this, we're somewhat effectively plotting the number of clusters in the data. And as we grow more and more data points, we're seeing more and more clusters. And Mike just made this observation that we think that the number of clusters should be logarithmic in the number of data points.
That's a proof by picture.
Yeah, and this is the best kind of proof by picture.
But if all the rows are equal, then it seems like very quickly by coupon collector, you collect a lot of them very quickly. It's not much.
So you'll even if they are large, in fact, even if they're not equal, if they're quite large, you'll collect a lot of them very, very quickly. But then you'll have that little bit of extra.
But
we'll get square root of n if it's
this is
uniform
square root n, yeah.
between all of them, not log n.
if
You're going to get log. It's the harmonic sum.
Not if it
they're
is
all equal
equal.
size.
It's coupon collector.
No, the hyperparameters of Dirichlet are equal.
So I will encourage you all to work this out during the break. Let's continue with this illustration for the moment. So whatever we believe about the rate here, I think there are two things that we can agree on. One thing that's happening is that the number of clusters is random here, right? So even if the rows weren't random, and we are drawing the rows random, row 1 through row k, even if they weren't, the number of clusters would be random. Because, for instance, even the second data point could belong to the same cluster or a different cluster. So in general, it's random. Another thing that we're seeing is that, in fact, it's growing with the size of the data. That's not surprising. We're going to be picking up these rarer clusters over time. And so can anybody tell me the asymptotic behavior of this graph, which I think we can all agree on?
Drops out at 1,000.
Yes, it's going to stop at 1,000 with probability 1. OK, so let's think about the implications of that observation. OK, so as we said, let me just first reiterate, the number of clusters here is random. We're getting a random number of clusters, and it grows with the number of data points. But it stops at k asymptotically. And sometimes that might be fine. Maybe if we have a set of data points that's much, much less than some k, we're never going to get up to that high number of clusters. But you can imagine cases where that might not be true. We don't know the number of species. There's definitely work on trying to estimate it, but it's not something that we definitely know. We don't know the number of topics that are out there. We don't know the number of groups in a social network that are out there. And so if we put some particular large k, if we want to get this growth in the number of clusters, if we want to get this randomness in the number of clusters, by putting some very, very large k on our model and saying we're just going to have a very large Dirichlet, we do run the risk of saying, well, maybe we were wrong. If we're too small, we might hit up against k. If we're too large, we might be using sort of a bunch of parameters that we didn't need to. It might be difficult to infer. So maybe we could know it, but maybe we don't. Sorry.
Just like a stupid question. So how much does it cost us if our k is much larger than we need to? Like somehow you don't talk about it.
Right. So one thing is if you were actually doing inference in this model, like turning this around and doing the Bayesian sort of inference model, you might think, at least on the face of it, that you'd have to instantiate every one of your latent parameters. You'd have to store them in memory. You'd have to update them in maybe your Markov chain Monte Carlo algorithm or something like that. And so those are all costs to your algorithm.
But do we understand, for instance, what is the number of samples we have to see, sort of to get actually? So is it just only purely computational, or also is it about the sample complexity that we need?
Right. So both of these are absolutely concerns, and I guess what I want to say is that what I'm trying to motivate with here is that choosing a particular k can be problematic. Ultimately, what's going to happen is we're going to decide right now, or I'm going to decide, and you're all going to come along with me, to choose k equals infinity, because we're never going to hit up against that end. But then we immediately come into questions like the ones that you're asking, which is, OK, but how do we actually take advantage of that? Because, of course, we're not going to want to store k equals infinity parameters or update k equals infinity parameters in finite time. And so we're going to want some approximation or some aspect of the problem that lets us only represent sort of what we need. And so this gets into questions that come up in actual inference. And the way that people deal with them, and I'll mention this briefly, and this will come up more in the later lectures, are things like marginalizing out the parameter and using a truncation analysis to know how close you can get to that parameter.
And By the way, like, so I guess this is a question for later, but I will ask it already. So somehow when you have this non-parametric Bayesian model, you can still apply it to data that comes from a fixed k parameter. So how do they, like, are they good at recovering the right k, or actually are they usually like...
Great, so this is a great question. Let's say I choose k equals infinity. Is this going to recover the right k?
Yes.
Well, let's think about it this way. If we choose k equals infinity, what's the assumption that we're making in the data? The assumption we're making is that there are infinity parameters. And so if we look at the growth that we just saw in the previous demo, that's going to go to infinity with probability 1. And so if you actually have a finite k, it seems like that's an undesirable behavior.
Let me kind of slightly correct there. So that's a consistency question.
Yes.
Suppose the real thing generated was k, and then we use this model. You still can get consistency under certain conditions.
Okay.
Okay, so in the prior, what Tamara's saying, yes, it goes to infinity. But in the likelihood, after I've got it generated from actual k underlying clusters, I can ask in the posterior, will I concentrate around that k?
But it depends what the consistency is. You can get consistency in the density, but if you do a Gaussian mixture model, you won't get consistency in the k.
Number. So there are conditions where you get consistency for some parameters and not others. It's a rich question.
Yeah, so there's this Miller and Harrison paper from, I believe, 2013 that talks about consistency in the number in, say, Gaussian mixture model, and there you won't get consistency.
Can I ask a slightly different question?
Yeah.
So in this thing, everything is sort of fixed model, but species are probably developing all the time. So is there a more advanced version of this?
Right. So yeah. So fundamentally, what we're doing here is we're doing something that's stationary. We're saying that the model isn't changing in time. And the usual way that people would start working with something that's non-stationary in a lot of these domains is they would say that this is a building block as part of a larger non-stationary model. So you would have, here's your stationary model. So for instance, something that might be done is maybe you're looking at all of the articles of nature. And the topics that people study in science changes over time. Every 10 years, we're going to have a totally different set of new problems in science that people are addressing. And so what you can do is you can have something like a Dirichlet process that is slowly changing its components. But you could think of this as being a building block within that model.
So the coalescence process from genetics is part of this overall scope. And so there you build a tree kind of with techniques like this that you branch at certain times. And then you have mutations along the tree. So, and then she would refer to the time varying version of that also, where the mutation rate can change and so on. So it's all part of the scope.
OK, great. So we've jumped way ahead, but let's go back to this idea of maybe we could choose k equals infinity just so that we don't hit up against this finite k. Now, at first glance, this seems like a really bad idea. Because after all, the whole problem with this was, maybe we had too many k, or maybe we weren't able to infer k. Although on the other hand, if we had streaming data and we're just not sure that we're ever going to hit up against k, this could still seem like a good idea. And so one of the big questions is, first of all, going to be, can we even do this? What are going to be the properties of this model? But then ultimately what we'd have to ask after that is, OK, can we actually do inference in this? And what is that going to look like? But for the moment, let's just say, let's go crazy. Let's try k equals infinity and say, what are the properties of this model? Do they have the properties that we want? So how could we even do this, first of all? How could we generate an infinity of probabilities that add up to 1? So let me first make an observation about the Dirichlet distribution that might prime us on how to do this. OK, so one way to generate the Dirichlet distribution is to go into your favorite software package and type generate from the Dirichlet distribution. Another way that you could do it is with a sequence of beta distributions. And so here's an observation. If I want a Dirichlet distributed random variable, it would be equivalent to first generate a beta random variable, and then generate the remaining mass proportions according to a Dirichlet. So this was basically an observation that was made earlier over here. OK, so what does this tell us? Well, here's a way that I could generate a Dirichlet distribution. I could take my whole probability mass, 0 to 1, and let's call that a stick. And I could break mass off of that stick. So first, I'm going to break off a proportion, which is beta a1, and then the sum of all the parameters minus a1. So I break off that proportion. So my first probability will be exactly that proportion. Now at this point, I have 1 minus v1 mass left in my stick. And I can do the same thing recursively. I can say, oh, well, that's just Dirichlet distributed. So I'll break off proportion a2 and the remaining hyperparameters. And so that probability will be 1 minus v1, because that was the remaining part of the stick from the first part. And then v2 proportion we took off here. Now I can do the same thing. At this point, I have a Dirichlet A3, A4, which is just a beta A3, A4. I can break off that proportion, What was left of the stick before I broke off this proportion was 1 minus v1 times 1 minus v2. And now I'm breaking off proportion v3. And then finally, I just have whatever's left over. So here's a way that I could have an infinity of random frequencies that sum up to 1. I could just have not stopped. So I'm going to do the same thing. I'm going to say, OK, a way to get a random number between 0 and 1 is a beta distribution. So I'm going to break off a beta distributed random variable from my stick, from my 0, 1 stick. Now, I have some mass left, and I'll break off another random proportion between 0 and 1 from that. And I'll call it v2. And so I take my remaining mass, 1 minus v1, from the first round, break off this v2 proportion, and I have my second row. Now I'll do this again. I'll say, oh, I've got some remaining mass. I'll break off v3, and I'll just keep doing this on and on forever. And on the kth step, I'll break off vk. What I had before the kth step was this, and then I multiply by vk.
What about the AI and BI? Are you like assuming something about their sum?
Right. How are you going to do this? OK, yeah, there's actually a few questions. So your first question is a great question. Probably we're going to have to assume something about the AI and BI in order to make this actually sum to 1. And so for that, I'm going to direct you to either your own solving of this problem or Ishwaran and James 2001 to think about what exactly would that constraint be. Because in general, this will definitely get us something that sums to less than 1. But we do have to make a constraint to make sure that it sums to 1. But actually, I'm going to take this even a step further and say, gosh, this would be a real pain in the butt to choose an infinity of these values. And so it would be nicer if we just simplified this drastically. For instance, by choosing all of the AKs to be 1 and all of the BKs to be alpha. If you don't agree with anything else, you must agree that this vastly simplifies that choice. This is what's known as Dirichlet process stick breaking when we make this choice. And in fact, to be more particular, the distribution over the rows, row 1, row 2, row 3, this infinity of rows, is known as the GEM distribution when we make this choice after Griffiths, Engen, and McCloskey's very early work in this area. Yeah?
So I have issues with the whole kind of direction. You were saying here is a very nice mathematical tool. It's rich, I can play with it, I can do all kind of calculations. But my goal was not to play mathematical games. My goal was to try to model some phenomena in reality.
Yes.
So can you say anything about why these Dirichlet processes is a good modeling of something in reality, not why it's nice to play with?
Great. So again, the goal, the modeling in reality, is to have a growing number of, and we're just thinking about clustering for the moment, a growing number of clusters as we get more data.
But that's not the only
Okay,
way
so let me jump in there a little bit. We'll get to that by the end. So it's like day 1 of statistics. We told you about the Gaussian distribution. You can say that's just mathematics. And I'll say, well, hold on a little bit, right? So for example, does this give you power laws? Because in real graphs and networks and stuff, you get power laws. It turns out not. It gets you heavy tails, but not quite power laws. So if you want power laws, can you do something more? So we'll do something more. We'll keep going. This is just the beginning of a longer story. But if you're going to do modeling, you have to have a framework and a mathematical tool to start. So the first step is a baby step. Does that help? Yeah.
So it seems like if you just put on the condition that sum of the A's over infinity is finite, then what you did before would work. Is that another way of doing exactly this?
But so let me step back from your question just a moment and say we would never want to have an infinity of parameters that we'd have to choose though anyway. Right. So if we actually wanted to use this in real life, we're going to have to make some vastly more simplifying assumption than just making some constraint on these.
So maybe there's another point. There was a question over there about why use the beta distribution at some point. So that's a very parametric assumption inside of overall non-parametric context. If you don't like that, you could put mixtures of beta in at that point, and suddenly you're non-parametric at that point if you care to, if you want to be rich there, or not. And similarly here, those A's you could make just put a single A and then put a distribution on that, which is typically done, a gamma. Right? You're being very parametric at that point. You say, no, you could put a distribution on A's and generate them from something more rich, like a mixture of gammas. So again, it's part of the modeling formalism to decide where you're going to put your energy of lots of richness or more constrained parametric kind of thing. And then depending on what you're trying to infer to, a lot of these are nuisance parameters you don't care about. You have to put in a model to get something that's a real model.
Okay, let's look at a GEM distribution.
One last point, I'll shut up here in a second, but GEM were geneticists, and they developed this framework because it literally comes out of the genetics. It's an actual good model of some genetic process out of the cohesive tree. So they weren't just plain math; they were actually doing genetics, and they discovered this math.
Okay, so here we're looking at a GEM distribution, and remember the way that we're generating it is we're first making a beta draw. In particular, here it's going to be a beta 110 draw because our GEM alpha parameter is 10. Then we're doing that again and again and again, and if only because these are going to have to be an infinity of probabilities that sum to 1, they're clearly going to get progressively smaller, at least on average. So my question for you now is, suppose that instead of a GEM 10, I draw a GEM 1, how is this going to look different? Right. So could you walk us through why that would be?
Well, if you draw the first one, it's already
It's going to be about half.
Right. So instead of beta 110, the first one's going to be beta 11. And in beta 110, remember, the second, the row 2, is bigger. And in beta 11, relatively speaking, the row 1 is bigger. And so we're going to get bigger jumps towards the beginning. And so in fact, we see that quite dramatically. There's still an infinity of rows here. It's just that this first one is humongous, and these are all extremely tiny. And likewise, if we choose 100, we're going to get a different sort of behavior. We're going to find that we get quite a bit smaller rows in the beginning.
But I cannot get jammed in the beginning, right? I cannot get jammed on the left.
Yeah, so if you choose 1 in alpha, and you can convince yourself that this is true, then these are almost surely going to sum up to 1. So you won't get to the point where you sort of stop here, and then you don't have anything left. Okay, so let's talk about how this fits into our mixture model, our clustering framework that we were building up in the beginning. We have a Gaussian mixture model. So previously we had said, okay, if we have 2 clusters, then we'll draw row 1 and row 2 from a beta distribution. Again, slightly abusing that notation. If we have k clusters, capital K, we'll draw them from a Dirichlet distribution. And now we've built up this GEM distribution, which is a generalization of that. We'll do the same thing. We'll draw our mu k's. We'll draw an infinity of them. I guess this is a little bit cut off. Yeah.
There's something that's confusing me. There seems to be sort of a permutation being factored out somewhere. So when you take a limit of these finite Dirichlets, these finite ones, each of the components will have the same distribution. But these GMs will sort of have to tail.
Right. So it's a generalization in some sense, but it breaks down in other ways. So it's not the same as having just a completely, symmetric Dirichlet. Although to be fair, it's perhaps more equivalent to having a Dirichlet with different parameters anyway, because if you remember the stick breaking that we did, a Dirichlet with the same parameters wouldn't have the same stick breaks as a GEM would. We would actually have different sticks. So we were breaking that symmetry already anyway. And you'd have to break that symmetry because you are going to an infinity of these. You're not going to fit all of them being equal.
Is it because you're going to sort of order the clusters in the order of...
But it's not about ordering. You're losing the order completely. You're just getting these different proportions. Another way to think about it, so if you actually look, so it turns out there's a way that we can integrate these out via the Chinese restaurant process. And this will actually give us a way to generate each cluster assignment without generating this GEM process at all. So we could do that. We could say, OK, here's my first data point belongs to the first cluster. My second data point belongs to the first or second, et cetera. We can make that generation. If you looked at the proportion of data points in the first cluster that appears, in the second cluster that appears, and the third cluster that appears, it turns out it's exactly the ordering in the GEM. So another way to think about it is this is some sort of size-biased ordering, that you just get this order of appearance, and then you choose those probabilities, and this would give you the GEM. But ultimately, when we're using this for clustering, we're losing the orders altogether.
let me say that a slightly different way, maybe because you are still puzzled. Suppose you have a Dirichlet with, K, huge, right, and sample from that. So you're getting a whole bunch of numbers that aren't in any particular order, that are kind of fluctuating, right? Sort them, all right? That's called the Poisson-Dirichlet distribution, okay? Now, given that decreasing sequence, sample from them. So you might get the first one, but you might not. You might get the third one, all right? It'll be a slightly smaller number, all right? Then maybe you get the second one, or maybe the fourth one, the first one. Now you're getting something that's kind of tending to go down, but it goes up and down. That's the GEM distribution. So size bias sampling of Poisson-Dirichlet, which is the sorted one, is GEM.
Yeah, that's why I was saying there is sort of, somewhere there is a permutation being factored out.
Yeah,
But
so we'll get to that later. We'll talk about D-phonetic theorem and permutations and all kinds of other, there's a bunch of stochastic process stuff you're not quite seeing here, but I hope you're getting a sense that it's there.
Okay, great. So we draw these means. Now, let's think about what we would do next at this point. So if we have this collection of means and this collection of probabilities, what we would do is we would say, okay, I have my data point, and I'm going to draw that data point from cluster 2 with probability row 2, and then I'm going to assign it to the mu2 mean. Okay, a completely equivalent way that I could have done that would be to say, okay, well, actually what I'm going to do is I'm going to draw it from the cluster with mean mu2 with probability row 2. And so I could have made a probability distribution that puts row 2 on mu2, rather than separating out choosing 2 with probability row 2 and choosing mu2. Incidentally, it turns out that this gets rid of some of the ordering issues that you were just describing, because now we actually end up having a measure that has a lot of nice properties, such as any particular region can have some nice near independence properties from the other ones. Okay, so if we describe this distribution, where we put probability row 1 on mu1, probability row 2 on mu2, et cetera, which is what I'm saying here, we'll take each row k and put it at the location mu k, this cluster center. This is actually what's known as the Dirichlet process. So we technically haven't described a Dirichlet process up until this point. This is an example of one. The two parameters that it takes are 1, the alpha parameter of the GEM, and 2, the base measure from which we draw the locations in the probability distribution. So what's going on here is these two lines, the drawing the GEM and the drawing these cluster locations, are equivalent to this line where we just draw from a Dirichlet process.
Question?
Yeah.
So the Dirichlet process, does it require the means to be Gaussian or just anything?
It does not. So in general, we're going to have a GEM with some alpha parameter, but this base distribution could be something completely different. So I could be doing something like topic modeling. It might itself be a Dirichlet distribution, maybe over words. Okay, so the next thing that I would do is I would draw categorical from my rows to say, oh, this data point belongs to this cluster. I would say, okay, this data point, the nth data point, is going to be somewhere around the mean indexed by Zn. But again, just as I said, these two steps are equivalent to this step. These two steps are equivalent to just making a draw from this distribution, saying this data point is going to be around the mean that I've drawn from this distribution. And because it's a discrete distribution, I'll get those means repeated a lot, and I'll get data points in the same cluster. And then finally, I'll draw my data points actually normal around the cluster center to which they were assigned, and that's what I'll get here. Okay, so let's do a last demo together. Okay, so I said a lot of things in there that aren't possible. So two of them are, I draw an infinity of means, and I draw all of the rows. So I can't draw an infinity of means, at least on any computer that I have access to. And I can't draw an infinity of row values, because that would take forever. So what could I possibly do? Does anybody have any ideas? Let's say I want to make draws from this Dirichlet process mixture model. I want to draw data from it. What could I do? Again, I love the hand pictures. Could you elaborate?
Well, I think you should, I mean, if you generate it in the way you built your graph previously.
So when I built my graph previously, I drew row 1 to row 1,000, and then I drew categorical draws from that distribution. And here I can't draw row 1 to row infinity.
The only thing that mattered about the new point was whether it was in an existing cluster or a new one.
Absolutely.
Do it on demand?
Yeah.
Yes, on demand. Great. Do you want to elaborate just a little bit more?
Keep drawing points on the line.
Great. Yes. So here is the key observation. Remember, the way that we drew from the GEM was I drew my row 1 to row 1,000, and then I made my uniform random draw on the line, and I said, oh, yeah, this data point belongs to the component that it fell into. Well, what I could do is I could do the same thing this time. I could draw row 1 to an infinity of these rows, and I could draw my uniform random draw, and it belongs to the data point that it belongs into. And this uniform random draw, a key point is that it's independent from all of these rows. These are completely independent draws. So instead what I could do is I could draw that uniform random draw first. I could keep drawing rows, because remember, the way that I get the rows is I could take a proportion and a proportion and a proportion, and I could stop when I'm past that uniform random draw, because I don't need the rest yet. And so this is what I'm going to do. So ignore what's going on down here for the moment and just look up at this GEM. I want to draw row 1, row 2, et cetera, from a GEM. And so what I'm going to do is I'm going to make my uniform random draw, and I'm going to keep slicing off beta components until I cover it. And that's enough to know that this data point belongs to this component. OK, now what's going on down here is along the way, I generated a bunch of rows. So for each one of these, I'm going to draw the mean of its cluster down here. And so in this case, I happen to generate 6 rows. And so I'll draw 6 means. And then finally, I'm going to draw the data point around the cluster to which it was assigned. And that's what I'm doing right here. And so this way, I didn't generate an infinity of means. I didn't generate an infinity of rows. It was all finite because it was on demand. And so I'll do this for another data point. And so it's a mean I already have, but I get a new data point. I'll do this for another data point. It's yet another cluster where we have 3 components filled in now, 3 clusters. 2 data points from the same one. And I keep doing this, and eventually, I'll have to generate some more. So we see that I generated another bunch of components there. And if I generate, say, 100 more data points, I'll generate even more. If I do 1,000, eventually we get to the point where we're not even seeing what's left over. And so after another, say, 5,000 data points, I've got 19 clusters that have been filled in. But as I do this again and again and again, I'll just keep getting more clusters at a rate that you can definitely calculate the rate of. Any questions about this?
So the means, how did he generate the means?
So the means here in this particular case, I drew them from a normal. So like I generated exactly from the generative model that we described earlier. So I choose a particular normal that's a little bit diffuse on this region and went from there.
So when you're there, you just generate the normal random variables with the point.
Yeah, exactly. Okay, so obviously this was just the beginning. We went through an example problem clustering and an example non-parametric Bayes model, the Dirichlet process. And hopefully we answered some of these questions that we set out to in the beginning that we want to learn more as we get more data. And the way that we're doing that is this growing number of clusters. And the way that we make that happen is an infinite number of components. And so the difference between the growing infinite number of parameters was the components versus the clusters, the latent versus the realized. OK, why is this challenging from an actual inferential perspective? Well, we have an infinite number of parameters. We're not going to be able to ever deal with that directly. But the reason that it's actually something that we can do inference with is that only finitely many of those parameters are realized in the data. And so that's what makes it possible for us to do pretty good approximate inference. So we're doing approximate inference anyway at the end of the day when we're doing any type of Bayesian, modern Bayesian model. And so long as any approximation that we make here is sort of on the order of the error that we induce from that, then we're good. So there are a few different approaches. One, for doing inference in Bayesian nonparametrics, one is to integrate out the infinite parameter. We'll be seeing that in Mike's talk about the Chinese restaurant process and similar ideas. And this is exact insofar as we have some conjugate models or something like that. Another option is to truncate the infinite parameter, and this was getting at some ideas that were brought up earlier, which is to say, can we find some maybe finite model that expresses what's going on in the infinite model, and perhaps in such a way that we get the right error that's on the order of the true approximation error at the end, so that we're not missing out on this growing aspect of the Bayesian nonparametric model. In fact, we can make it adaptive and have it grow with the size of the data. OK, great. And so we'll come back for the remaining lectures and dig deeper into sort of the wider world beyond Dirichlet processes next. Thanks.